We also can do two free surfaces. You have phi from the bottom, phi in the top zone here, take its limit from below. Phi in the middle region here, take its limit from the top, little q from the bottom below. And you get three non-local equations. One we talked about earlier. This time we have beta is the free surface on the top, and eta in the middle. So beta t and eta, beta, p and q. P and q, again, p and q capital Q. You have non-local equation, another non-local equation. This comes from essentially Green's theorem here and here yield these results. And then you get two pressure conditions because they're two free surfaces. Even though it looks like it's hairy, if you write down the fundamental equations, they balloon out because you've got to solve velocity potential equations, Laplace's equations, and all those equations. This is so much simpler. And from this, we can get intermediate Benny-Luke, intermediate Benny-Luke, intermediate Kadamsa-Fish equations. You get integral relations. I'll talk about that part, the intermediate wave part, at Dave Benny's session. Benny session, Dave doesn't notice, but it's a session. Okay. A few words about nonlinear optics. I have, how many minutes did you say?
15 minutes.
15 minutes. You've been such a good audience. I can't do that to you. I can't keep you here 15 minutes. We'll try to keep it to 10. I'll just have a few words about optics here and communications and lasers. In '73, researchers found the nonlinear Schrödinger equation minus waves and fibers, Asagawa and Tapper. Motivated by this, Mollenauer in the 80s started doing experiments on we call classical solids, using them for communication purposes. Well, in the 80s and 90s, people began saying, well, in one fiber you can send many signals in different frequency channels. And when you do that, there are going to be some interactions. And the interactions could be devastating. So that came to suggest the concept of dispersion management, which is used in practice, and it's very nice mathematics. So I'll tell you a little word or two about what we did, going back to the work with Gino Biondini, and then we use this in many of our subsequent works in communications, but then I evolved in this line of research to lasers, and you'll understand why. Dispersion matrix system. Well, here's nonlinear Schrödinger equation. If D and N were constant, this corresponds to the nonlinear Schrödinger equation comes out of water waves, nonlinear Schrödinger equation that people have studied in empirical systems. But in dispersion magnetic systems, you have D naught as an average and a large, rapidly varying term. You have an anomalous and a normal region, delta 1 and delta 2, N of Z cosine damping amplification. Average of delta 3. Their pulse width is about 10 picoseconds. So here's a figure. You send in a signal, it goes to an amplifier. Then there's an anomalous fiber and a normal fiber. That's what dispersion management does. They're very large and rapidly vary in the scales of the fiber. Well, we studied it by perturbation theory. I'm not going to go through the details, except to say that we found a nonlinear integral differential equation representing this problem where you factor out the fast scale. That allows you to get a whole lot of insight. Here's sort of the equation for the slow problem. UZ, it's a Fourier space, omega squared average, you have and then an average term which can be written as a double convolution. If this is a constant, then you get nonlinear Schrödinger for you get an integral equation to represent solitone solutions. Here's a classical solitone. Here's a dispersion matrix solitone. So the net result is that we introduce multiple scales. A fast scale Z over ZA. ZA is the amplifier length. And a slow scale Z. And then from that, you get to leading order a linear problem, which you can solve in terms of rapid exponential and slowly varying amplitude that satisfies the integral differential equation. It seems everything I do these days has integral differential equations somewhere. Be that as it may, you get solitone solutions. This is a dispersed solitone. When you do the averaging, you basically only see the peaks. So you just average over all these guys. Well, what does that have to do with mode lock lasers? So I got a phone call from one of my colleagues in Boulder in the mid-2000s, seems like yesterday, said, well, we have this system in our lab, and we think there might be solitones. Well, you look at this, what do you see? You just see a bunch of green, red, blue. It doesn't make any sense. Well, you send in a signal, it goes to a crystal, a sapphire crystal, excites the signal. It goes to a mirror, goes to a prism pair, back, and some energy is expunged. You get a pulse train. Well, this crystal has very, very strong negative dispersion. The prism pair that they decided on, independent of communications, has just the opposite dispersion. So you're set up for dispersion magnetism. That's really what happens. You get a dispersion magnetic system out of this configuration, and out of these things, the claim is you get dispersion magnesolitones. But there's some wrinkles. It's not trivial. So we worked with Steve and Boaz, his student Kusia Marashi, and we developed some theory. And the theory was the following. With Steve, it was just this equals 0. It's exactly the communications problem with rapidly varying coefficients. So we had the math, everything was fine. But then it became clear that we got good results, but we couldn't explain one thing. Many things, for sure. One thing in particular, the concept of mode locking. That's my last remark here. You see, what Steve did is for many different average dispersions, we could see it, took measurements, and we compared the theory that those lines, those curves, the theory to these different experiments, 2, 4, 6 experiments for each average dispersion. And we felt it was reasonably good agreement for this level of approximation. But we couldn't explain why the laser, what happened is you have this little box, this little table, they tapped the system and it locked into the mode. We couldn't explain mode locking. And that's the purpose of all these other terms. It's called the gain, the filtering, and the loss. The gain term has an integral denominator. We say the gain is saturated by energy. Because when you go through the crystal sees the signal and it raises the energy. It raises the signal according to the energy, so it sees the energy. There's filtering because there's a window, a frequency that the crystal sees. And then there's loss because some energy is immediately lost, or some amplitude actually. It's a chopping more or less. And it's approximated by this. Well, when you do this, here's typical calculation, the typical numbers. You put in some gain, fix the other parameters. Gain small, system take initial conditions, the pulse decays. For gain large enough, the pulse locks into a mode. So you take a fairly general initial condition, and for sufficiently large gain, it locks. And it locks into one solid time, well approximated by nonlinear shrinkage. Whether you do dispersion management or not, you get locking due to those extra terms. Mathematically, it's novel in a sense because you have non-locality intervals and you have saturation due to intensity. What we call this the power energy saturation model, and not been widely studied, although if you go to the literature you can see hints of it around. Certainly House had the key ideas, but he expanded this in powers of P. So I'm pretty much going to end here just to say you get a novel kind of equation, you can explain mode locking, and you also get it in the normal region, not just the numbers.
Can you show the master equation for 1 second?
Yes, the master equation. This is the master equation. So you take the communications problem, gain and filtering, you take the power term and expand it one order. And this is what House worked with because it was easier to get special solid true-wave solutions to that equation. But you don't find mode locking for a reasonable range of parameters, very narrow range of parameters. So we didn't use this equation because it doesn't really explain the mode locking that they find almost all the time. So let me go to conclusion. I apologize for all these intermediate things I don't know. A lot to say. But I didn't say.
How long did you think you will have?
Well, I use this as a prototype lecture to take pieces because I'm giving many different lectures. You're right, but if I really mean, I go through it all in an hour. Depends on my mood, but today I was just 60th birthday party. It's time for celebration. Water waves, reformulate. The problem is a non-local, we call it non-local spectral system, non-local equation with a parameter cap. We can get interpolations, asymptotic reductions, and extend to multiple fluids. I talked about high-order systems a little bit on internal waves. Optics, nonlinear Schrödinger equations play a central role. Dispersion management systems are important, and they're important not only in communications, but also lasers. I didn't talk about photonic lattices. That's another line of our research, and it's clearly not appropriate to talk about here. Thank you for your attention.